colleagues, students, and colleagues from industry, external colleagues. So if you haven't met me before, my name is Chedly Tizaoui. I am the Associate Dean for Research, Innovation and Impact for the Faculty of Science and Engineering. I would really like to, I would like to state that the senior leadership team of the university is on an away day today. That's one of the reasons why you don't see the Vice Chancellor. Whenever he is around, he normally attends these meetings. So it's not you, it's an away day of the senior leadership team. So I am going to do the whole thing today. So briefly, I think this is an important occasion for especially those who are recently promoted within the faculty. We started the inaugural lectures, I think if I remember correctly, Sam, around 2019, and then lockdown, yeah? And then kind of we restarted now this year. I think we are really engaging all the newly promoted professors. So this is an occasion we celebrate as a community the achievements of you, Chedly, with friends and colleagues. So this is a fantastic opportunity for us to listen to Chedly's work. And before I hand it over to you, I would really like to say a few words about Chedly. Chedly is a professor in the Department of Chemical Engineering, and he leads the Water Resources Research Lab at the Faculty of Science and Engineering. His research focus, as probably most of you are aware, it's a very important area, water research, especially advanced oxidation and separation processes to address challenging issues related to water and resources, including the removal of micropollutants and valorization of waste. Chedly started his academic career in West Yorkshire. Hopefully we'll hear a little bit more about that.
Lots of curries there.
And after a short stop in Midlands, he joined Swansea University in 2010. It's a remarkable journey. He is passionate about developing innovative technologies that can improve the quality of our water and environment, very important area, while reducing the impacts of waste. I'm really delighted to have you, listen to your talk soon. Chedly, it's all yours now. We're looking forward to listening to your talk.
Okay. Thank you, Arasu, for the Thank you, Arasu, for the introduction. Thank you all for coming to join me today and listen to a few of the things we do here related to water and the environment. And I'll start. So I'll try to shine some light today on water and trying to focus on micropollutants and emerging contaminants, which are issues that perhaps they are ignored to some extent, although not to the industry and other research communities. So I'll explain to that. You could guess this little molecule there doing a bit of a gym there. That's ozone in action, and that video is for non-thermal plasma, which I'm going to talk about in a minute. So what I'm going to talk today about, I'll give you an overview about our research interests in my group. I'll also give some introduction about the global water challenges, and I'll focus mainly on the micropollutant challenge and advanced oxidation processes, and I'll give some results from the research we did over the past years, and finally some conclusions. So our research really has a broad remit across various aspects of the water, mainly focusing through two types of processes from a chemical engineering point of view, advanced oxidation processes and separation processes. And I try to percentage our contribution to those both themes. That's roughly our contribution in terms of publication on oxidation and separation, about nearly half-half. The aim to do that is to address several challenging issues related to the water, such as water and wastewater quality, the emerging contaminant problem, environmental protection. We did several projects related to oil removal from industrial waste, looking at hazardous chemicals, metal issues in water. And also, recently, over the past couple of years, I had quite a good grant looking at circular economy and valorization of waste. That's capital fund grant. So we have a range of equipment that we could use for this purpose. The area of water comes under the umbrella of SDG 6, if you are familiar with the Sustainable Development Goals by the UN, and number 6 is related to water. Our research lab, so we cover fundamental and applied, really covering both, focusing on several oxidation techniques, mainly ozone. I've been working in ozone for so many years now, and I'm asset editor of the Ozone Science and Engineering, which is the only journal that focuses on ozone research, covering the European, African research related to ozone. But we apply those technologies in the water and also to protect the environment. The snapshot really of some of the projects and equipment we have in the lab. In the COVID-19 as well, we tried to apply ozone to address the issue, and that received quite significant interest from the media and other stakeholders as well, looking at application of ozone to disinfect ambulances and buildings. This gives you a snapshot really of the areas we do on advanced oxidation, like photocatalysis, catalytic ozonation, hydrogen peroxide, and non-thermal plasma, which I'm going to talk about later. Separation, membranes, filtration, coagulation, flocculation, adsorption, ion exchange, and so on. So there are a number of techniques we use under the umbrella of separation process, and that's snapshots of the papers published in those areas. Water. Water is vital for life. We know that, all of us. We can't argue about it. Yeah, it is also vital for our food, for the production of our food. It is extremely important in the manufacturing industry. Yeah, energy. The nexus water energy is very well established. Water affects energy. Energy affects water. Climate, ecosystems. And obviously, water on the larger is a human right, and also is linked to the economic benefit in a country. Yeah, if a country is lacking water, the economy in that country would be struggling. So water is important for life. It is a human right, but also it has a huge impact on the economy in any country. I'm not going to go through all the world's water challenges, but to give you an idea here, some of the challenges that are related to water, and that picture tells a lot of stories there. You can write a book by simply looking at that picture. And some of the challenges are related to the water are, for example, cited here. 1.7 billion people live in water-stressed areas. By 2050, there are predictions that 5 billion people could be affected by water shortages across the world. 80% of the world population live in areas with threats to water security, and that threat can be the availability of the water. It can be also linked to the quality of the water, but also can be linked to flooding. And in the UK here, although we have plenty of water, but there are risks associated with the flooding. 3 in 10 people of the global population, they lack access to safely managed drinking water. And what is worse, that 6 in 10 people, they don't have access to proper sanitation. And that's extremely important because all the diseases that can result from that are very, very significant. There are nearly 2 billion people still use sources of water contaminated with pathogens. And 1 million of people die every year because of that exposure to the pathogens. On a larger scale, water is unsustainably managed. There are issues with the management of water. Even in the developing world, it's the same. The story more or less is there. There are challenges around the management of the water. Obviously, it's unevenly distributed across the world. Nearly 900 million people still practice open defecation, and that's as well another extremely important problem related to the water. Another aspect about this story, in the developing world, households the most affected by water issues are women and children. And that impact will have on the education of those, in the career, and so on. As an example, from Sierra Leone, for example, here, which is an African country, women and girls, they lose approximately 200 million hours each year just simply to fetch water. Okay, we are blessed here perhaps to open the tap, you have water, but other places there are huge impacts. This is on a global aspect of the water challenges, but also the developing world, there are also huge challenges related to energy, related to the quality of the water, related to the processes, related to the management, and we have a colleague here from industry who could tell you more about the issues that they face in the water. Because of the importance of water, the UN allocated one of the Sustainable Development Goals, which is related to water. Every year, more or less, they assess how the world is developing in terms of the water, what they are doing. And the current year, the UN predicts that in order to reach the targets they set by 2030, the world has to work much harder, 4 times harder, in order to achieve that target. If the pace goes as it is now, by 2030 you will have 1.6 billion people still lack safely managed drinking water, 2.8 will lack safely managed sanitation, and 1.9 billion will lack basic hand hygiene facilities. And all that is related to the water. So there is a lot to do really in order to achieve those targets set by the UN. It's not only Africa or parts of Asia that are affected by water, it's everywhere people are affected by water. In this map, for example, shows the level of pollution that exists in beaches in the UK, and you can see there is quite significant number of beaches there are polluted. On a global aspect, 80% of the world's wastewater is being discharged into the environment without any treatment. And you can imagine the impact that would have on the environment. Another aspect of water now, investors, before they invest in whatever new project, they consider water as another risk factor they need to look at carefully, whether be it availability, whether be it the quality of the water. In the US in 2016, you have about companies, they reported 14 billion US dollars in water-related impacts. So it's quite significant, whether be it they maybe polluted the water and they received fines. So all these negative impacts, if you count them, cost the companies 14 billion in 2016. So that's a general overview. I'm going to touch base on one aspect of the challenges that are related to water, which is the micropollutant challenge or issue. Yeah? What are they? In the world, we have over 350,000 chemicals and mixtures that we use almost every day. They are registered, they are produced, and they are used. As you can imagine, those chemicals, they will end up somehow into the environment, whether it be in the air and mainly water. So micropollutants are all those chemicals that end up in water. Generally, their concentration is extremely low. We talk about micrograms per liter and even nanograms per liter. That's 1/1,000,000,000 of a gram in a liter. And these chemicals, they end up into the water. The list of those chemicals keeps growing almost on a weekly basis. There are new chemicals that are becoming important from an environmental point of view because of their impact in the water, or humans, or the aquatic life in general. So micropollutants, they are classified as pharmaceuticals we consume. Yeah. The pharmaceuticals people take, maybe 60% of it, maybe 10% of it will be used by the body, and the rest will end up in the wastewater. Industrial chemicals, pesticides, the surfactants we use at home, every one of us will wash, yeah? And then those surfactants, they are classified as micropollutants because of their impact. Personal care products, and importantly, steroid hormones, which are very potent substances that are found at extremely low concentration, nanograms per liter, but their impact is quite significant. Why we bother about these? Because they cause all sorts of issues in humans and also animals. They can disrupt the endocrine system. They can cause feminization of fish, for example, which was, in fact, that's what triggered the research in this area. In English rivers, they looked at, there was an issue in the 80s, 90s, and the fish becoming more females, and start to ask questions, why that? And simply because there is a discharge from a wastewater treatment plant that is discharging those hormones. Fish get exposed to the hormones and they became more females. There are studies that link the exposure to these substances to learning, for example, disabilities and difficulties, cancers, bacterial resistance. This is one of the biggest problems of these substances in the environment, is the antimicrobial resistance, which I'm going to give it a bit of interest. Antimicrobial resistance, I'm sure you all heard about this problem, and is generally caused by exposure. One of the pathways is not only related to those micropollutants, but one of the pathways is exposure to these antibiotics in the environment. Some data there, like 70 billion prescriptions per year worldwide of antimicrobials. Obviously, people, they don't consume them all. Some of them they will throw in the water. And so the main point here is, out a large proportion of those prescriptions, they will end up into the environment, contaminating our waters, okay? And by exposure to these substances, bacteria will develop the resistance to the antibiotics, in simple terms. There are currently 1.27 million deaths in 2019 that are linked to drug-resistant infection. And that can go up to possibly 10 million, yeah? By 2050. This map shows, it's a recent research, in fact, Nature Communication this year, shows the distribution of the resistance across the world. Yeah? The aquatic contribution is quite significant to that resistance, but the resistance can be found everywhere, even on the skin of people. They take samples on the skin of people and they discover that resistance, even on the skin, can develop. Is the problem new? The answer is not. So since the 1950s, some research start to make some noise about exposure of animals and the environment to these substances. However, that really did not go far, perhaps for various political reasons, but certainly there is also the technology is not there, particularly to measure the substance. And one key, important key, is early of the year 2000, late 90s, at the beginning of the 21st century, year 2000, 2001, 2003, etc., there were a huge development in the analytical techniques, HPLC, for example, mass spectrometry. Therefore, researchers were able to analyze the concentration of these substances in water at extremely low concentration. So there were methods being developed around this area, and Therefore, the research start to grow significantly, and you can see the increase from early 2000 for research related to micropollutants in water and wastewater is increasing almost at an exponential rate. There is a bit of dip there. That's possibly due to the COVID-19. One of the papers I mentioned about the fish that is becoming females by Susan Jobling, looking at the widespread sexual disruption in wild fish. And that paper is quite significant. Okay, how we get exposure to these or how they end up into the environment. All of us in the morning take showers, go to toilets, there are hospitals, industries, etc. And on a daily basis, what you do, you use water. The minute you use water, this substance can end up into the water. And what's happened to these substances, they will be transported from the homes to a treatment plant. And that treatment plant is quite a large wastewater treatment plant. Unfortunately, those wastewater treatment plants, they were designed many decades ago, and they were not designed to remove this substance. So what's happened there is that wastewater comes to the treatment plant. That wastewater contains these substances. Some of these substances may biodegrade there, and that's fine, like aspirin, for example. Some of them, they will biodegrade, but proportionally, so partial degradation. And some of them, they will persist. They won't biodegrade. Nothing will happen to them. They come in, and they can come out from the treatment plant to the natural environment, and that natural environment can be a river, can be groundwater, or sea. Okay? There are other issues as well. Some industries, whether it be deliberate or by mistake or whatever, they may discharge that wastewater into the environment directly. And I make reference here to India. A lot of antibiotics are produced in India, and the villages around the industries where they produce, no antibiotic can help the population there, because the amount of the wastewater that is contaminated by those antibiotics from the pharmaceutical industry discharged into the environment is quite significant. And bacteria is clever, develop the resistance. So anyone from that village have an infection, no drug will be effective against it. So that wastewater can end up into the environment. The other issue, some of these structures of the sewer pipes, they are quite old, like Victorian type sewers. And these, they have cracks, they are not properly maintained. So what's going to happen, they will end up leaking their content into the environment as well. So the overall picture of all of these is that you will get water also from these sources to produce drinking water. Yeah? And that drinking water will be treated in a treatment plant that is also not designed to remove these substances at the nanogram per liter level, and therefore that micropollutants will end up into the water we drink. I'm not frightening you here, but this is something that is happening, okay? The other issue with the micropollutants is that the wastewater that is treated there may be used for irrigation, to irrigate the food, okay? And what's going to happen, those micropollutants, they find their way, pharmaceuticals, antibiotics, etc., they find their way into the food we eat. Also, wastewater, they have biosolids, and that biosolids has a lot of nutrients and generally is used also to spread on land. And therefore, that also another source of these micropollutants. So they may end up into the food we eat. This research from Spain shows that human exposure to micropollutant via fruit and vegetable consumption is about 9.8 micrograms per person per week. You may think in the UK we don't practice this, but we are not safe because a lot of food being transported and came from Spain and other places in the world where wastewater is used to irrigate those food. Okay, so the main conclusion out of this is that wastewater treatment plants, they play a major role, or they are the hotspot really for the release of these substances into the environment. If the problem is there, what's the regulation there? What's the regulatory position or the policy? This problem started, particularly I mentioned the year 2000, when research started growing, and the wastewater industry and the regulator became aware of the issue, and regulations start to emerge to control these substances. But really didn't go much around the year 2007-8. You remember we had the economic crisis across Europe, and that caused some delays on this. So the regulator did not really push for this to be properly regulated. But instead in the EU, what they created this watch list of priority substances. And the watch list is basically asking the wastewater companies to take samples and measure the concentration of a list of substances and keep it on the record, basically. But they don't have to treat it. Because if we aim to treat these substances in water, the water bill will become huge. Okay? So there is that issue as well. However, the only country in the world, I think, that pushed for regulation around this is Switzerland, where their wastewater treatment plants, they've been upgraded with new technologies to remove the micropollutants from water. And one of the technologies, in fact, it's the technology that has been selected, is ozone and activated carbon to remove these substances. Yeah. Also in the UK, there were a lot of research that started, and we had the national demonstration program, and also found that ozone was a cheap option to adopt for the removal of micropollutant from water. So if the economy goes better, perhaps we'll have a regulation that is forcing wastewater companies to treat these substances and not let them discharged into the environment. Okay, advanced oxidation. I think I don't have much time, so I'll try to skip this quickly. Advanced oxidation is, by definition, it's any process that would generate this species called hydroxyl radicals. They are extremely potent oxidants, and any process that can generate those radicals in a sufficient quantity to affect water treatment or purification then is classified as advanced oxidation. To give you an idea, these species, their life is about few nanoseconds. So it's very, very short-lived. Yeah? It's not something you can make and take from one place to another and give. But there are examples of processes that produce these hydroxyl radicals, and here the list of it. You combine different oxidants together, and they can produce those radicals. And ozone-based AUPs are quite significant, and they have interest from industry and research community as well to address those challenges. Why ozone? Ozone because it is a highly oxidant substance, and it's the highest one compared to the traditional oxidant we apply in the water. Is even more potent than hydrogen peroxide, chlorine, and chlorine dioxide. It reacts through two mechanisms, direct reaction and indirect reactions. The direct reaction is that the molecule of ozone itself is oxidizing other molecules, but the indirect, it dissociates into water and produces these hydroxyl radicals. Then it becomes an AOP. I'm not going to go through all that data, but just to give you examples of the importance of ozone and its oxidation power through looking at the values of the rate constants there. And you can see the rate constant for the hydroxyl radical are much, much higher because they are more powerful oxidants. Yeah? But their concentration can be small into water. Ozone is also a strong disinfectant, so it can be applied as an oxidant to oxidize those micropollutants, but also it can disinfect the water. And as an example here, if you want to destroy this bacteria, E. coli, I think, 3-log destruction of that bacteria, you can see if you take, for example, E concentration of 0.01 milligram of various oxidant, for ozone it takes less than a minute. For chlorine dioxide, that goes maybe about 50 minutes, and for silver, nearly 1,000 minutes. So it's more effective disinfectant. This is a very interesting point as well about ozone. For example, it can kill cholera virus very quickly in less than 0.5 minutes. We used it to also kill SARS-CoV-2, and was extremely effective. Its rate constant is 10 power 5, which is very high. The technology is established. What you need is a feed of oxygen, an ozone generator, which looks like that, and a contactor where you dissolve the ozone into the water. That contactor is about 7 meters deep in the ground, by the way. Yeah. And then for safety purposes, you need a distractor before discharging the gas to the environment. Okay, I'll give you a few examples of work we did to degrade these substances using various technologies of our research. One of the micropollutants we looked at are the endocrine disruptors, estrone, 17-beta estradiol, and 17-alpha ethinyl estradiol. These two, estrone and estradiol, these are naturally occurring substances. Humans, they generate them and they end up in the toilets and then in the wastewater. This one is extremely potent substance. And it's the main ingredient in the contraceptive pills. So this molecule is extremely difficult, first of all, to degrade biologically, but also the impact of it is quite high. I'll give you a few innovative processes we looked at. One of them is this, what we call LLO, liquid ozone system. And in this process, we take the ozone, which is a gas, and we dissolve it in a solvent, okay? And then we contact the water with the solvent, and then we obtain treated water and a solvent being separated from the mixture. The reason for doing this is that generally micropollutants are hydrophobic substances, so they have tendency to distribute more into a solvent, okay, than water. And this solvent is selected in a way to dissolve ozone at extremely high concentration as compared to the water, 10 times, yeah, to give you an idea. So what you end up here is a system that is highly concentrated ozone there, and a system that is capable to extract those substances from the water. And then you have two mechanisms for their removal by extraction, liquid-liquid extraction, and reaction. And I'll show you the kinetics later on that resulted from that. This work was done in Yorkshire. I was in West Yorkshire with Yorkshire Water, where we collected samples from sewage treatment work, Marley sewage treatment work. And then at that time we had to develop the methodology to analyze these substances. As I said, they are in the order of nanograms per liter. So we needed quite a sophistication to be able to analyze them. That's the analytical method. And this is the extraction of these substances into the solvent. And we can see they distribute well into the solvent. And the effect of pH here, that distribution is not affected until about pH 10. And that's fine, because the pKa values of these molecules is around 11. That means if the pH is below, say, 11 or 10.5, 10-ish, they are neutral molecules. If it's higher than that pKa, they ionize, and therefore they become more distributed into the aqueous phase, and that is described in there. And this is extremely important. So by applying the new technique, which involves liquid-liquid ozone, the kinetics of removal of these substances, the three of them, is almost instantaneous. So the first sample we could collect from the experiment, we obtained none of them because they were extracted and oxidized with the ozone. This process was also costed and simulated, and we obtained a total cost for using this technique. It's around 0.1 pound per million liter. Capital M is million, not milliliter, which is quite good compared to the National Demonstration Program figure for ozone, which was around 4 pounds per million liter of water to be treated. Okay, this is a very conservative estimation of the cost, but still, even if it is like 10 times that value, it's still competitive compared to the other. That's some publication there. This is another work. We looked at triclocarban, which is an antimicrobial, and this triclocarban is found in the soap that you use as an antimicrobial chemical. It's specifically added to the soap and lotions. It was developed to be used in hospitals and so on, yeah? But because of those problems, its use starts to be less and less. However, it has its cousin, if you want to. It's called triclosan, and they do the same job. So either that or that, they are found in soap as an antimicrobial substances. However, research found that this exposure to this chemical can cause endocrine disruption in the same manner as the other ones, and also antibacterial resistance. So there is interest in degrading this substance. We did some work with ozone as well, and we can see that simply using ozone was extremely effective in removing this triclocarban as well from water. Obviously, there are a bit of chemical engineering there. You see all these equations for mass transfer that is combined with chemical reactions, Hatta number, and so on. So no need to go through that. But if you are interested, I teach this in Sepro too. But the main point in there is that ozone, again, is effective to remove this substance from the water. Another example, herbicide clopyralid, which is a highly mobile herbicide in the environment. Why? Because it's soluble in water, and therefore it can be transferred from one area to another quickly, and that's why it is highly mobile. But it is stable against hydrolysis and photolysis, and can cause contamination of groundwater and surface water. We used photocatalysis, for example, to degrade this substance, again obtaining the optimum catalyst concentration in solution, looking at the effect of radiation, looking at the time it takes and the kinetics, and so on. Another example is diethyl phthalate, and diethyl phthalate's everywhere. Even now, you are touching diethyl phthalate, possibly, because it's in plastics everywhere. Yeah, and it's quite a serious endocrine disruptor that is also found in almost every sort of environment. So with this, I'm not sure what's happened. Yeah, okay. So for this, we used nanocatalytic ozonation, and here we combined ozonation with carbon nanotubes. Why we use carbon nanotubes? Because carbon nanotubes can produce those reactive species I've been talking about, like hydroxyl radicals, through the contact between carbon nanotubes and ozone. So that can lead to the formation of these highly oxidative species. Yes, we developed, obviously, there is a bit of kinetic work there on homogeneous and heterogeneous reactions and combining, because the two, they develop in the process. So we described that mechanism and came up with that equation that was published. Importantly, by adding carbon nanotubes, that increases the degradation of this phthalate by about 22%. Hybrid ozone membrane, this is another area been doing work on. It's we make membranes, CEDAR will be making membranes of this sort, and combine them with ozone. Yeah. So that's Regina's work, if you know Regina. Yeah. And Juno as well. I'm not sure, maybe you guys don't know him, but they left both. Anyway, importantly in there that the application of ozone with those membranes enhances the flux and also enhances the rejection of the substance that we are removing. Non-thermal plasma. How much time I have? 10 minutes? Okay, non-thermal plasma. So what is it? Non-thermal plasma, this came from an EPSRC grant I had a couple of years ago where we built the equipment and developed this area on the research. It's basically you apply a high voltage, and when I say high voltage, it's high. It can reach up to 30,000 volt, yeah? Between an electrode and the surface of the water. So you have, I'm not sure if you can see that, that is the ground. So that piece of metal there is the ground, and the top there is the high voltage electrode. And through this application, what's going to happen, you will produce a cocktail of reactive species within that environment. And those reactive species will diffuse to the water, and they will do the oxidation that we want to achieve. So in simple terms, high voltage, you have high energy electrons. They collide with the molecules, disintegrate them to produce reactive species, and those reactive species can be diffused into the water and oxidize all the substances there. The type of oxidants you produce, one of them is ozone, hydrogen peroxide, the various radicals, ultrasound, shock waves, UV. So you get really a nice mixture of these oxidative species that can be useful to treat the water. So this is the system, how it looks like. That's the system in the lab. These are some of the characterization that we need to do, particularly looking at the current and the voltages that we measure. And the work we did for this is we collected samples of wastewater from Gowerton, wastewater treatment works, not very far. I'm sure you know Gowerton. It's about a few miles from here. And also developed various analytical techniques to do the analysis and so on. So I'm not going to repeat the same story there. But importantly here, we wanted to look at the degradation products, because so far I'm telling you that we have a molecule, we degrade it, and that's it. But what's happened to that molecule, that's another story, because you may produce other molecules that can be more toxic. So we wanted to look at what are the byproducts that are formed. We have the analytical capabilities to measure these molecules using LC mass spectrometry, triple quad. But that triple quad will generate a huge amount of data, millions of data points. So we developed a MATLAB code that processes that data automatically to only extract the significant masses of interest to us. Okay, and all that will be automated, kind of. Traditionally, people spend maybe weeks looking at these data to extract the information. So in here, it can be automated. And we support our analysis using molecular modeling, like density function theory, using Gaussian, to give some insight into the kinetics and the type of byproducts being formed. Some of the results here, this is like the voltage and current waveform that we produce out of the experiment. We calculate the power that is being consumed there by multiplying frequency by integration of IV dt. And importantly there, you see that the power, that's the average power, it's not constant. It would change over time. The reason for that, because when you produce all these reactive species, they change the properties of the water. And therefore, the amount of current that is passing through the solution also changes. So the water becomes more conductive. But in all cases, our integration of all these powers over time gives us the energy that is delivered to the system. And that's the money you pay if you are doing this operation. We also analyzed the reactive species produced, such as, for example, the conductivity there. The pH keeps changing, generally becomes acidic pH. The amount of ozone produced, hydroxyl radicals, hydrogen peroxide as well produced. And we looked at the degradation of the substances. You remember those estrogens, E1, E2, and EE2, using DI water and also real wastewater. And the kinetics, in fairness, did not change much between the wastewater and the DI water. There is obviously some change because of interference from other substances in the wastewater, but it's not that far. We looked also at the energy that is used in the process as function of the removal percentage. Here, ethinyl estradiol as an example. Yeah. Degradation product. So I mentioned that code will generate this sort of graphs automatically, and we can look at what mass would change over time to give us the byproducts that is formed. I'm not going to show all that, but just these are examples. And this is, for example, one of the degradation products of 17-beta estradiol, where the reactive species attacked that function of the molecule. Okay? And we can look at its change over time. Another area that I'm interested in and been doing some projects, this is one of the projects we had. It's the GCRF funding to develop technologies for water treatment in affected countries like Africa and so on. So we had this project, SOS Water, and this is basically to develop a solar system to treat the water using the solar energy. And those experiments, they were done here. You may recognize this lab, it's C0001, and we have the solar panels just inside the lab and facing the sun, and it gave result. And this water being treated in roughly less than 20 minutes if we change the voltage. And all that was done by solar energy there. COVID, very quickly, I'll touch on this. Yeah, that's the rapid response we had. So we had the ambulance project when we looked at its disinfection using ozone. That was during the COVID period. We have paper that is in Journal of Hazardous Materials, if you want to look at it, with Cardiff University, where they did all the testing of SARS-CoV-2 over there. And we can see ozone was very effective, 710 power 5, the rate constant by which ozone attacks that virus. This also was the first paper that was more theoretical, initially looking at the ozone as a potential oxidant for COVID-19. And then we had a couple of other, even one of them with Arasu on the modeling side of the ozone. So in conclusion, I'm not going to repeat what I was saying, but 2 points to remember. there are too many water challenges to address in the UK, in France, in Germany, in the US, in Africa, in Sierra Leone, in wherever country you think about. There are too many challenges. Perhaps it's the type of challenge that differ, but every country would have challenges related to water. And we should not take water for granted. There are a lot of issues there to think about. Acknowledgement, some of the funders are there. Students, this list of my PhD students, RAs, current students, visiting researchers on the back, I, for some reason didn't show, and some of the collaborators as well. Thank you. So do you have any questions?
Thank you, Chedly. I think it's remarkable and fantastic. I learned a lot. And
excellent.
Hopefully we'll have some questions, but not too many.
I knew you were going to ask something, yes.
So the solvent we're using, is it carbon-based? Because why doesn't the ozone just react with the solvent?
Yeah, very good question. So it's not carbon-based, right. It's siloxane-based. So ozone does not affect it, keeps stable on it for some time. But that's one of the areas we like to look at. It's after long exposure of that solvent to the ozone, are there reactions that would take place? Theoretically not, but yeah, we need to prove it.
Yeah. So is that like, does it not mix with water?
Does not mix, yeah, that's a very good
So
point
is
as
it
well.
emulsion then?
Like oil.
So do you mix it up in emulsion with small droplets?
So the idea is should not be mixed. This is the rig, in fact. We yeah, that gives you an idea about this. So that column there, the solvent will come from the top and the gas ozone from the bottom. So that solvent gets saturated, and then we introduce the wastewater at that point there, and they will mix in this about 10-meter long reactor. And we have some static mixers to mix the two together, the aqueous phase and the solvent phase.
Thank you, Chedly. I also learned a lot. Thank you. So now you need to take something that is present almost at the nanomolar level to what level then?
Yes, very good. So there is a lot of research, in fact, going in that area to determine what we call the PNEC, the potential non-effect concentration of each of those substances. You can do it in a single component, and then you find, for example, to give you an example of these, estrogens, about 1 nanogram per liter. Yeah? But if they are in mixtures, they may not add up those PNECs. Now, to answer your question, it would depend on the molecule we are looking at, yeah. And there is a lot of research going on to find the values of the potential non-effect concentration for each of these substances.
Oh, my next question, we shouldn't keep asking questions.
I think we'll
yeah, it's fine.
Yeah.
Outside.
Okay.
During the refreshment session, because we have another lecture coming up after this. Yeah, so I think perhaps we can continue outside. Is that okay, Enrico? Sorry.
Yeah, absolutely.
Yeah. Apologies, yeah.
No, that's all right.
Because we are running out of time. So can I quickly thank our speaker, Chedly. It's not just for speaking or getting the promotion. Overall, obviously supporting the faculty, the way in which you are supporting, COVID response, fantastic research, and so on. So we are really grateful for all your support you are offering to the faculty. I would like to thank you all for coming and supporting. Especially I would like to thank Kelly Bevan and Sam Board. They actually put these programs together. I don't even know what's happening. So before we actually conclude, I think the faculty normally commissions a small sort of a prize, if you want to call, to for the memory of this day for you. So it's a Welsh crystal engraved with your name.
Excellent.
Right? It's not in gold, but it's a fantastic thing to actually keep it as a memory. So I'm really happy to present this to you, Chedly.
Okay, thank you. Thanks. Thank you. Good.
So
looks like this.
We can actually meet outside for the refreshments. And so if you're staying for the next lecture,
fantastic.
great to see you again.
Thank you.
We'll take some snaps.
Okay.